Hannah, thanks. Time for our chemistry lesson this morning. We have Jesse Miller with us, a U of I Teaching Lab Specialist, REACT Program Director. All right, Jesse, what's on tap?
Water. Yes, I know. Did I boom? And I have a cup of water here. And this is really a cheesy joke too, right? I got my cup of water. I make joke, you know. In Soviet Russia, joke tells you. So, so this is water, okay? H2O, right? We're all familiar with or most of us are, through grade school science, that water is composed of hydrogen and oxygen. And this is illustrated here. You got the red oxygen and you got the two hydrogens on here. Now these are kind of neat, these little models, because it shows some of it helps you visualize some of the unique properties of water. Water is a very light molecule. I mean, an oxygen and two hydrogens is not a heavy molecule. It's only about 18 grams per mole, or 18 atomic units. Compare that with ammonia, which is about 17, or methane, which is about 14, or 16, excuse me. It's pretty small, but the boiling point and the freezing point for water is a lot higher than either one of those things. Okay, and you might say to yourself, why would that be, Jesse? Well, I'll tell you.
Why would that be, Jesse?
Oxygen has a large negative charge. Hydrogen has an okay positive charge. When you put these on here, and the way the molecule is shaped in this kind of V shape right here, puts what we call a partial positive charge on the bottom, in the way I'm looking at it, and a partial negative here on the top. So you have this dipole moment, or a magnet. It's like a magnet. And so when they bind, like when water binds to itself, it will bind what we call a hydrogen bond, which is this hydrogen to the oxygen. So the positive portion of the hydrogen bonds with the negative portion of the oxygen, and that gives it a stronger force. If it's held together more strongly, it's going to be more difficult to break those bonds, and so water going to gas, steam, takes a lot of energy, which is why it's so 100 degrees centigrade to boil it, as opposed to other small molecules like methane, which is a gas at room temperature.
Sure.
So it's what we call hydrogen bonding. There's a few other molecules that have this. Water is probably the smallest one that really does this hydrogen bonding. And we can see this magnetic property of water with your little prop there. Okay.
Oh, I thought I was just getting the party started.
Your pink balloon. What I need is you to get a static charge on that. Rub it on your coat or rub it on Cynthia's head.
No.
Yeah. Okay. And then I'm going to put the stream of water going. And I want you to put the balloon up to the water. Don't touch it, though. Up to the stream.
Okay.
And you'll see what goes on here. Okay, you ready? All right, we'll get a stream going. And you can see the water's bending.
Cool.
If you get a bigger charge on it, it'll bend more. So let's go do that again.
Sure.
All right. Let me use my shirt.
I paid 19 people to work on this hair in the morning, Jesse, and I'm sacrificing it all
There
for
we
you.
go. All right.
Oh,
there you go. You can see the water bending, and that's because of the magnetic properties, or this dipole moment that exists in the water, and it's attracted to the negative charges on the balloon that you get from the static. So it's kind of cool. It's just kind of a neat little experiment you can play around with at home. Most people don't realize that water is actually attracted by magnets and static electricity. Yeah, and so because of these properties, like I said, water has a high boiling temperature, relatively high for a small molecule. It has a relatively high freezing point for a small molecule. I mean, within our temperatures we have on Earth. Like methane and freezing point is way down there, where you'd have to use liquid nitrogen in order to freeze it. I'm not even sure you can freeze it with liquid nitrogen. And ammonia and small molecules like that are just, because the only forces that are really holding them together are what we call London dispersion forces, and they're not very strong. So they're able to escape easily. As a matter of fact, ammonia escapes our atmosphere quite readily. So does methane. So anyway, that's kind of an interesting property of water. We're gonna talk about some more properties of water in the next segment, but they take too long to set up, so we're gonna have to vamp.
Take a break and set up, eh? Good stuff.
All right, Jesse, thanks so much for joining us this morning. We are going to have more from you in the 7 o'clock hour, WCIX, of course.